హాయ్ ఫ్రెండ్స్, వెల్కమ్ టు జిఎంకే ట్యూటోరియల్స్. ఇప్పటివరకు ఎవరైనా ఇంకా మన ఛానల్ సబ్స్క్రైబ్ చేసుకోకుండా ఉంటే ప్లీజ్ సబ్స్క్రైబ్ అవర్ ఛానల్ ఫర్ లేటెస్ట్ వీడియోస్ అండ్ ఆల్. Okay, so thank you for your support up to now. I'm really thankful to each and every person, whether directly or indirectly supporting our channel and promoting us also. So today we are going to discussing about the image processing sequence video. That is nothing but minimum mean square filtering. It is also called as a WIENER filtering. Generally, this WIENER filter is nothing but generally error is the one important thing. So the main purpose of the WIENER filter is nothing but in inverse filtering we are not considering the noise parameters. Just we are not taking any considerations of the noise and the characteristics of the noise, but we will take the noise consideration. That is nothing but statistical characteristics of the noise is also take into the consideration to estimate the undegraded image. So that is a basic thing. So generally, the main method of this nothing but noise and random variables. The objective is to find the f dash of x comma y from the g of x comma y. So generally error means that what is the meaning of error? So generally error means that error is equal to, error means that output image, the difference between the output image and the input image. So error square is equal to expectation of f minus f cap whole square. Okay, whole square. So this is a measure of error. Okay, this error measure is given by like this, where expectations is the value of an argument. It is assumed that noise and image are uncorrelated. Okay, so the frequency domain representation, frequency domain representation is nothing but f dash of u comma v is equal to h conjugate of u comma v into sf of u comma v by sf of u comma v into modulus of h of u comma v whole square plus Sn of u comma v into g of u comma v. So this is the equation for the frequency domain representation of the error function. So moreover, it can be represented as g of. So we know that generally modulus of h of u comma v whole square value is equal to h of u comma v into h conjugate of u comma v. So for that purpose I have to represent so moreover just I have to take the so in this equation just I have to take sf of u comma v is a common in numerator and denominator. So take these two values are common values. We can represent the equation as h conjugate of u comma v by h of u comma v whole square plus Sn of u comma v by sf of u comma v. Why? Because sf of u comma v means that here we don't have any sf term, sf of u comma v in the noise term. So that's why I have to take multiply and take it in the denominator. That's why the numerator term is a common value, then denominator value placing same like this. So here into g of u comma v. So from this property just you have to take some adjustment. That means that multiply. So in this equation, multiply with h of u comma v in both denominator and numerator. So by multiplying these two variables in the numerator and denominator, the above equation can be represented as 1 by h of u comma v in the numerator h of u comma v whole square. Why? Because so this is multiplied with h of u comma t, it becomes as a h of u comma v whole square mod square by. So this adjustment is similar to like this, by modulus of h of u comma v whole square plus Sn of u comma v by Sf of u comma v into g of u comma v. This is nothing but f cap of u. F cap of u is nothing but expected value of the information. Okay, so this is the finalized equation for Wiener filter. F dash of u comma v is nothing but expected value of the or maybe restoration of the undegraded image is equal to 1 by modulus of h of u comma v, modulus of h of u comma v whole square by modulus of h of u comma whole square plus Sn of u comma v by Sf of u comma v. So suppose if you are taking k is equal to, suppose if you are taking k is equal to Sn of u comma v by Sf of u comma v, the previous equation can be represented as f dash of u comma v value is equal to modulus of h of u comma v whole square by 1 by h of u comma v into moreover h of u comma v whole square plus k into g of u comma v. So from the previous discussion here, the product of complex quantity with the conjugate is called equal to magnitude of the complex quantity square. So this is generally called as a Wiener filter. So that means h of u comma v. So that means where we use the fact that product of complex quantity with its complete h of u comma v whole square is generally called as Wiener filter. Is known as this result is this quantity. This result is called as a Wiener filter. Complex quantity gives rise to modulus. So this result is known as a Wiener filter. Moreover, the terms inside the brackets is also commonly called as a minimum mean square error filter. So this within the bracket terms is also called as the terms within the minimum mean square filter. It is also called as a minimum mean square filter or else least square error filter. It is also called as a least square error filter. These are the different names. So these unknown terms can be represented as here, that is nothing but h of u comma v. So h of u comma v is equal to degradation function h conjugate of u comma v is nothing but a complex conjugate Moreover, modulus of h of u comma v whole square is equal to h conjugate of u comma v into h of u comma v, as well as Sn of u comma v is equal to modulus of n of u comma v whole square, that is nothing but power spectrum. Power spectrum of noise. At the same time, S of u comma v is also called as modulus of f of u comma v whole square, that is nothing but power spectrum of undegraded image. Undegraded image. So these are the some of the observations from this equation. Okay, let us move on to the next one. So the signal to, if you want to estimate the quality of the noise, if you want to estimate the quality of the noise, signal to noise ratio is a SNR, that is nothing, signal to noise ratio, that is nothing but summation u is equal to 0 to m minus 1, summation v is equal to 0 to n minus 1. So modulus of f of u comma v, it is nothing but Fourier spectrum. So Fourier transform undegraded image minus 1. At the same time v is equal to 0 to n minus 1 modulus of n of u comma v. So this is nothing but signal to noise ratio in the Fourier spectrum domain. So SNR in power spectrum. SNR in power spectrum. At the same time, mean square error can be represented as MSE, mean square error is equal to 1 by Mn, the formula. So summation x is equal to m minus 1, summation y is equal to 0 to n minus 1. Modulus of error can be represented as f of f my error square is equal to f minus f bar whole square, right? So f is nothing but two-dimensional image, f bar is nothing but f cap of x comma y whole square. So that is nothing but mean square value. Therefore, signal to noise ratio in terms of in the spatial domain, signal to noise ratio in the spatial domain is equal to signal to noise ratio in the spatial domain. Signal to noise ratio in the spatial domain is equal to summation x is equal to 0 to m minus 1, y is equal to 0 to n minus 1 to f cap of x comma y whole square by this mean square value. So that means mean square is equal to formula of this one. That gives rise to signal value of a complete signal to noise ratio in the spatial domain. This is nothing but SNR in spatial domain. So this is nothing but a Wiener filter. Okay. So if you are taking the certain times, we can also call it as a sometimes square root of these measures is also called as a root mean square signal to noise ratio and root mean square error also. So this is nothing but just a brief introduction about the Wiener filter. Why we are considering Wiener filter? Wiener filter is very